Hello everybody, welcome back. We have an ionic compound AB formed. Charges on those ions can be plus minus 1, plus minus 2, plus minus 3, or even larger. What does that mean? Basically saying this can be any binary ionic compound, A and B. So what are the factors that determine the charge of an ion in this compound? So it looks like they're asking what's going to determine A is going to be plus 1, plus 2, plus 3, and B is going to be minus 1, minus 2. What's going to determine the charges? Well, the answer can be a million different answers, starting with a very fundamental, the number of protons versus the number of electrons. You can talk about the radius, the radius of the atom or the ions, the size. But I'm going to look at two factors, and you're going to have to try to visualize this in terms of energy. So the first one I'll do is ionization energy. And that's the ionization energy, and that's the energy required to remove an electron, outer electron, from an atom in its gaseous state, or atom or ion in its gaseous state. I'm just going to abbreviate that IE. And the second one is going to be electron affinity, and that's the energy change. I'll do EA. That's the energy change involved in when an atom or an ion gains an electron. So you can say it's desire for an extra electron. The reason I'm looking at these factors is because you need ionization energy to produce more positively charged particles, cations. And you need electron affinity to produce more negatively charged ions. And actually, let me throw in a third term. Sorry. So I'm going to do three factors. Let's get rid of this. Some of this. All right. So the third factor we're going to need is lattice energy. And this is the one that has to overcome these negative terms. Well, this one's going to be unfavorable, not negative. I'm sorry, unfavorable. And this one could be favorable or unfavorable. But in any case, the lattice energy has to overcome any unfavorable energy changes. And by the way, lattice energy is the energy change. Let's do this here. It's the energy change when ions in its gaseous state turn into that AB. That's what we're looking for, that solid ionic compound. All right, so for any of these scenarios to happen, this term here has to dominate these other two terms. Otherwise, it just won't happen. Okay, and so when we draw an up arrow that's unfavorable, it's endothermic, and down arrow is favorable. So let me show you using, let's do this. So sodium and fluorine. So sodium is going to require some amount of ionization energy to remove its one valence electron. It won't take a lot of energy because it only has one valence electron. So an up arrow might be something like that. And fluorine actually would like to gain an electron. That's electron affinity. Right. It has a relatively high nuclear charge, and gaining one will get that full sublevel. So that is energetically favorable. We want down arrows on an energy diagram. Now when fluorine turns into fluoride, one negative, and sodium turns into the one positive cation, those two are going to be attracted. And you're going to get some amount of lattice energy that's going to it's going to dominate. So that's why we know sodium fluoride forms one positive, one negative ions. Hold on, I'm going to get the diagram from our textbook. Okay, So I know there's a lot on the screen, but just cut this screen in half and look on the right side. Just focus on the right side. So here, just want to highlight those three things. So here, ionization energy to require sodium's 1 electron in its gaseous state to turn into that 1 positive cation is going to take 495 kilojoules. All right, so that is going to require energy. Now over here, fluorine, when fluorine gains an electron, so neutral to 1 negative, it's actually favorable. It's exothermic. It releases energy. That's good. But if those are the only two components, only two factors, this would not happen. Because you see the up arrows, it requires more energy. So once this becomes 1 negative, and once the sodium becomes 1 positive, then the Coulomb attraction that lattice energy dominates. This is very favorable. So it's going to happen. So overall, you're starting here, you're ending up here. This, when you have, so that's why sodium and fluorine form 1 positive, 1 negative. Now, going back up here to this periodic table, once you remove sodium's 1 electron, you're into the core of sodium's electrons. You're not going to get, well, the energy required to remove the second electron from sodium is going to be off the charts here, because it's already got, the core electrons are already even more attracted to the nucleus. So this term, going back here, after the first ionization, the second ionization energy is going to be magnitudes greater. And yes, if sodium does form 2 positive cations and fluorine forms 2 negative anions, yes, the lattice energy, you would expect it to be greater, but it wouldn't be great enough to compensate for this huge amount of energy required to remove sodium's core electrons. That's why you're only usually dealing with valence electrons when you talk about ionic bonds. Okay, and the opposite reason for fluorine to gain 1 electron is energetically favorable. It would like to do that, but it's not once it's already fluoride 1 negative, do you think it wants to gain another electron? Not only that, all by itself in a whole new energy level? No, that's going to be very unfavorable. So that down arrow is going to turn up arrow really fast. Okay, so the whole point of me saying that is that's why you wouldn't expect sodium and fluorine to make any of these other charges. You would only expect sodium and fluorine to produce ions, 1 negative and 1 positive. All right, so let's take a look at one example where we have charges 2 and 1, 2 positive, 2 negative. All right, so that's the other side of this graphic. Magnesium and oxygen. Right, magnesium is right next to sodium, and oxygen right next to fluorine. So we have good comparison here. So it's going to take some amount of energy. It's always going to take energy to remove an electron. So we're talking about ionization energy here for magnesium. Right. Now, after it loses its first electron, we got to strip away another one. That second one is going to be even harder. So you would expect the ionization energy to remove 2 of magnesium's electrons to be much more than the energy required to remove sodium's 1 electron. All right, and then even more once you get in the core. So we're not even talking about that because we know that's not going to happen. Naturally, it's not going to happen favorably. All right, so now let's look at oxygen. Oxygen, to gain 1 electron, that's energetically favorable. Not a lot. But once oxygen has gained an electron to become a 1 negative anion, do you think it's going to want to gain another one? You might say, yeah, because then it looks like neon. That part is true, but electrons repel each other. So to add the second electron is going to be energetically unfavorable. It's going to require the input of energy, endothermic. All right, so to get the 2 negative anion, which we have to get, it's going to require some amount of energy. So we got an up arrow and an up arrow. But the thing with this is magnesium, the 2 positive cation, and the oxygen 2 negative cation have a lattice energy that dominates. It's just huge exothermic step. Let me show you. If I can get my, here we go. I'm gonna have to zoom out so you can see this whole graphic. All right, so here we have, look at this. This is the, oh wait, okay. This is the energy required to ionize 2 of magnesium's, the magnesium is both valence electrons. Okay. And here's the energy required to add 2 electrons to oxygen to make it 2 negative. All right, the first one is slightly favorable, but the second one is unfavorable, and then if you add those 2 up, you get this 737 kilojoules of energy required to get that oxide anion. But now we've, if you use Coulomb's law, right, Q1, Q2, all right, over this bottom term doesn't really matter, because now you're doubling the Q's, 2 times 2. This is that lattice energy is going to be about a factor of 4 than what it was for this sodium fluoride. All right, so look at that lattice energy. It's very favorable. It's going to, it's exothermic, almost 4,000 kilojoules of energy, right, lost by the system, and that's going to make it so much more stable. So that's energetically favorable. That's why magnesium and oxygen in magnesium oxide, the ionic compound, is made up of 2 positive and 2 negatives. Right? And again, it wouldn't be 3 positive, 3 negative, because then you're going into core electrons from magnesium, and then you're adding into new energy levels for oxygen. All right? And it wouldn't be this either, because then the lattice energy wouldn't be enough to compensate for the ionization energy from magnesium. So I hope that made it a little bit clearer. This question is a little bit vague, but I think that's what it wanted.